Okay, hi guys, it's Mary here. Please excuse the low video and audio quality. I had to get this equipment at last minute in order to get these videos to you in time for you to study for your exam. So basically we're just going to be going through some of the more complicated questions in the tutorials just to help give you guys an idea of how to tackle the questions when you reach them in the exam. So for this first video we're just going to be focusing on the migration question that you saw in tutorial 2 and in tutorial 4. Yeah, okay, so let's do that. First things first, don't be worried about this question. It's written with lots of words to freak you out, and there are quite a few components to the questions, but it can be broken up very easily into two separate parts: before migration and after migration. So the question states that capsaicin sensitivity, which is being able to taste the hotness of chilies, is determined by a single gene with two alleles. The dominant allele allows sensitivity to capsaicin, and the recessive allele allows insensitivity to capsaicin, so you can't taste the hotness. So it talks about here 50 elephants in a Tanzanian population. Sorry, let me get it to focus. Okay, so we have two populations. Tanzanian one, and that has 50 elephants. And we have a Zanzibar population. I can't spell. And that has 15 elephants. Okay. In the Tanzanian population, it tells us that the dominant allele, which is capital C, but we're just going to use P and Q for now so that people don't get confused. So the dominant allele P has a frequency of 0.47, and the recessive allele Q has a frequency of 0.53. In the Zanzibar population, they say that there are 15 elephants, but only one elephant is capsaicin insensitive, which means it has a genotype it has the homozygous recessive genotype. Therefore, if we assume, and only if we assume Hardy-Weinberg equilibrium, that we can square root that to find our value, our Q value. So if we're looking for our Q value and we know that it's the square root of 1 out of 15, then we find that to be 0.2582. Okay, with that we can find our P value, which is the inverse of that. I'll let you work it out. Oh, yeah, right. So first things first, we need to understand that these are two separate populations which existed before the migration event. So first we have to determine the sink and the source population. In the question it says that the Zanzibar population was moved into the Tanzanian population, which means our source is the Tanzanian population and our sink is our source is the Zanzibar population and our sink is the Tanzanian population. Okay, right. Then we need to break down what happens after our migration event. So, let's have a look. There's the way you were taught in class was too fiddly. There were too many parts to it. But here I have an easier way for you to do this. And that uses this formula, which you've all seen before, so it shouldn't be too much of a problem. Q final is equal to QM times, what is it? Times M, yeah. Plus 1 minus M times Q initial. You all should have seen that formula before. Sorry, I hope the camera is staying focused. Okay, let's break it down. What is QM? QM is your Q value of your source population before migration. So that's your Q initial of your source population. And in that case, that is 0.2582. Right. Our M value is the proportion of the sink population that was originally the source population. Okay, so that would be the individuals that came from the source population, so the number of source individuals, over the total sink population after migration. So after migration, you're going to have the Tanzanian and the Zanzibar populations together. So it'll be the number of sink individuals and the number of source individuals. So that gives us 15 over 65, which should be 0.2308. For these kinds of questions where you got lots of fractions and decimals and stuff, try and stick with 4 decimal places at the end and only round off when you get to the end of your question. Otherwise, you'll get inconsistent results. Okay, now we have all of these other things, so let's substitute them into the equation. So Q final is equal to 0.2582, right? Yes. Times M, which is 0.2308, plus our Q initial, which is, your Q initial is for your sink population, and this Q final is also obviously going to be for your sink population after the migration event. Okay, so that Q initial is equal to 0.53 times 1 minus M, which is 1 minus 0.2308. Okay, and that will give us a final value of 0.4673. This is our Q final. This is the Q allele frequency of the population after the migration event, which is made up of the Tanzanian and the Zanzibar population. This means that our P final for the source sink population is going to be 0.5327. Now, the question asks, if these elephants bred, how would the arrival of the Zanzibar elephants have changed the number of capsaicin-sensitive elephants in the Tanzanian population in the next generation? So because we've already assumed Hardy-Weinberg equilibrium, we can say that between generations, the total number of individuals does not change and the allele frequencies don't change either. So we can just use the values we have here. So how do we find the number of individuals in the next of each genotype in the next generation? So obviously our capsaicin sensitive individuals are going to be made up of the P squared and 2PQ individuals, and that can be calculated by using these values here. And that can be calculated to, what is it? Capsaicin. Sorry, I'm just looking through my notes here. Right, so that'll end up, you will work it out, that there'll be 51 individuals that are sensitive. How do I get this? Sensitive, sorry. How do I get this value? I calculate the genotype frequencies given my P and Q values and times it by the total number in the sink population, which is 65 individuals. Okay? Now that leaves us, if we have 65 individuals, then we are going to have 14 individuals which are insensitive. By the end of it. Oh, that's correct. Sorry. Okay, how has this changed? Well, originally in the Tanzanian population, because that is our sink population, we had p-values, I'm not going to write it down, of here. How do we find the individuals that were sensitive and those that weren't sensitive? Well, we do the exact same thing. So this is after migration, and this is before migration. So the number of individuals we will see that are sensitive will be the same thing here. Okay, sorry about that. I made a little mistake. I actually didn't make a mistake, but I wrote this down wrong. So before the migration event, there were 50 individuals in the population. You must remember that. You mustn't make this mistake, which I did. Otherwise, it won't make any sense. Okay, so considering that there were only 50 individuals to begin with, sorry, you can see here, we will work out that the original number of individuals that were sensitive, if you calculate this, will equal to approximately 36 individuals which are sensitive. And thus, there will be, 14 individuals which are insensitive.